In this video, we're going to continue to study logarithms, and we're going to specifically look at how we can simplify logarithmic expressions and expand logarithmic expressions using certain properties. And eventually those will help us in solving equations, solving application problems, and things like that. Alright, so here's a list of the properties of logarithms. These first four right here we've already studied, and so we're not going to talk too much about them in this video, but these last four we have not covered yet. So let's take a look at them. So number 5, what it says is that if you take the logarithm of the product of two expressions, then you could have also just taken the logarithm of them separately and then added them together. Okay, so it might be kind of an unexpected property logarithms would have. So let's take a look at a little proof for this. So what I'm going to do is I'm going to take the logarithms on the right side, and I'm just going to give them a name. So I'll call the log base b of a, I'll call that x, and the log base b of c, I'll call y. Alright, so we know that anytime we have a logarithmic expression, we are able to rewrite it in exponential form. So the exponential form of the first one is b to the x equals a, and then this one b to the y equals c. So looking at that, what we see is that if I multiply a and c, then that's equal to b to the x times b to the y, of course. But then we know from our exponential rules that that's the same as adding the exponents. So now if we turn our attention back to this property, if we start with the left side, the log base b of a times c, we know that that's equal to the log base b of b to the x plus y. But now if we go back to property number 3, which we've used before, we can see that if the bases match here, then what's left over after you take the log base b of b to the x plus y is just x plus y. And that's all you have left. But what are x and y? X and y are these individual logarithms. So this is a pretty straightforward proof of something that might be a little counterintuitive, that we can add these two logarithms and that gives us the same as the log of the product of a and c. Number 6 is saying something very similar, but what it's saying is that if you divide a and c, that's the same as subtracting them. Okay, and so what I'd appeal to you with both 5 and 6 is really they are just kind of versions of our exponential properties that say multiplying like bases means you add the exponents, and dividing like bases means you subtract the exponents. Because remember, what a logarithm is it's the number you raise b to in order to make what's on the inside, right? So it is an exponent. All right, so I won't bother to prove 6 because it works pretty much the exact same way as 5. But then number 7, let's take a look at that one. So number 7 is saying that if you take the log base b of something raised to a power, then what you can do is just take that power outside, multiply by the logarithm of just that original base. All right, so this one, again, let's do a little proof for this. So what we'll do is kind of similar to the last one. Let's go ahead and let the log base b of a be equal to x. Get rid of that. So the log base b of a is equal to x. Right? Then we know that b to the x equals a. Right? Just rewriting in an exponential form just like on the last one. Alright, so what we can first say then is if you take b to the x and raise it to the r power, oops, that should be an r, excuse me, to the r power, then that should be the same as a raised to the r power. But then by our rules of exponents, we know that b to the x raised to the r is the same as b to the r times x, and that is also equal to a to the r. And so what this tells us is that if we take the log base b of a to the r, then that's going to be equal to the log base b of b to the rx, which again, by property number 3 up here, means that we just end up with r times x. But let's remember what x was in the first place. It was the log base b of a. So there's a nice little proof of number 7. And then finally, number 8 is what we call the change of base formula. And so what it says is that if we have the log base b of a, that I can pick any logarithm base that I want, and this will be equal to the log of that base of a divided by the log of that base of b. And we'll see this in practice later, but basically the reason we do it is so that we can convert a logarithm into either common logs or natural logs, because these are the ones that we use most often. So one of the things that we'll do with these properties is use them to combine logarithms into single logarithms. All right. So if I take an example 1 here, the log base 6 of 4 plus the log base 6 of 9. Sorry, this should be a 6 here. Because the bases are the same, and let me just emphasize from that previous page that it's really important that the bases are the same when you're trying to add or subtract them. But if the bases are the same, then property number 5 told us that we can just go ahead and combine this into a single logarithm by multiplying 4 and 9. Now in this particular question, we have the added benefit that when I do multiply 4 and 9, I actually get a number that is a power of 6, and so I can go even further. So remember what this means is we're saying, what number do I raise 6 to in order to make 36? Okay, which is 2. And if at first you didn't remember that, what you would do is say log base 6 of 36 equals x. 6 to the x equals 36, and then you would realize, oh, if I raise 6 to the second power, it makes 36. So that's why our answer is 2. So combining logarithms in this case allowed us to actually get it down to a really nice number, whereas neither of these are at all nice numbers for us to look at. All right, let's look at example 2. A little more difficult here because now there are coefficients in front of our logarithms. And again, let me take us back to the previous page. On the previous page, please notice that any time you are combining logarithms with addition or subtraction, there is just a coefficient of 1 in front of the logarithms. Okay, so if there's anything besides 1 in front, we cannot apply this rule. However, number 7 gives us an idea of what to do if we do see coefficients in front. We know that we can bring that factor up into the exponent inside the logarithm. So in both of these, our first step has to be to get rid of the 1/2 and get rid of the 1/3 that are multiplying by our logarithms. So we would first say this is going to be the log base 3 of 36 raised to the 1/2 power minus the log base 3 of 8 raised to the 1/2 power. And both of these actually, raised to the 1/3 power. This is a 1/3, so it comes up as a 1/3. Now, in this case, both 36 to the 1/2 and 8 to the 1/3 are actually nice numbers, so we can go ahead and simplify. 36 to the 1/2 is the same as the square root of 36, which we know is 6. And 8 to the 1/3 is the same as the cube root of 8, which is equal to 2. All right, so just remember that in general, if you have x to the 1 over n, that's the same as the nth root of x, right? So that's the property we're using there. So in this first case, I can take the log base 3 of 6 and then subtract off the log base 3 of 2. And then lastly, we have the log base 3 of 6 divided by 2. That's what property number 6 said that we're allowed to do, which can be simplified to the log base 3 of 3. But this, of course, is just an answer of 1 because we're saying, what do I raise 3 to make 3? Well, you raise it to the first power. All right, so here's a more challenging one for us to take a look at. So we have 1/3 times 2 times the log of 8 minus 3 times the log of 3 minus 2 log of 2 plus 2 log of 3. And let's just remember that when I don't have a base specified, that means that the base is 10, right? So over here, log of x just means the log base 10 of x. All right, so I want to be able to combine these, but I see first that I've got these parentheses, so I really want to untrap these from parentheses so that I'm able to start combining them with other things. So we'll go ahead and distribute our 1/3 through to both of these terms. So 1/3 times 2, we get 2/3 log of 8 minus 1/3 times 3, so this will be minus the log of 3, and then minus 2 log of 2 plus 2 log of 3. And then I have a whole bunch of coefficients in front here that I'd like to take care of. So I can get rid of those coefficients if I put them up as exponents. This one is okay, I can leave that alone. But this, I'll put my 2 up, so this will be minus log of 2 to the second plus the log of 3 squared. Now let's just look at 8 to the 2/3. On the previous example, we saw that 8 to the 1/3 was equal to 2. Okay, the thing to remember about 8 to the 2/3 is that this is the cube root of 8 squared, right? Is one way to look at it, or it's equal to the cube root of 8 squared. So you can write this either way, because generally what we say is that x to the m over n is the nth root of x to the m, or if you'd prefer, you could just take the nth root of x and then raise that to the m power. So if we look at this one, the cube root of 8 is 2, right? Because 2 times 2 times 2 is 8, and then of course 2 squared is 4. So this one I can rewrite as log of 4 minus log of 3 minus log of 4, right? 2 squared is 4, plus the log of 9. And I see that I have a log of 4 and a minus log of 4, so that's going to give me some nice canceling here, right? And so then the only thing that I want to emphasize here is that when you have negative log 3 plus the log of 9, just don't fall in the trap of not looking carefully enough at what the property says. So if I back up 2 pages here and look at number 6. Number 6 says log base b of a minus log base b of c is log base b of a over c. So the key here is that it's not about which one comes first or second, it's about the positive one goes on top and then the negative one goes on bottom. So my positive one's coming second, so this is going to be the log of 9 over 3, right? Because the 9 was the positive logarithm, the 3 was in the negative logarithm. So all that just collapses down to the log of 3. All right, and then just one last combining example where we're simplifying. So here we have the log base 6 of 72 plus the log base 6 of 2 minus 2 log base 6 of 12. All right, so we can first of all take care of this coefficient here so that all the logarithms just have a 1 as a coefficient. So this would be minus log base 6 of 12 squared. So here I can combine these two with multiplication. 72 times 2. And here I can calculate 12 squared, so that's 144. But then 2 times 72 is also 144. So what we have here is a situation where we started off with this expanded out logarithmic expression, but in the end, it's all just 0. Okay, so definitely worth our time to simplify it. All right, so going the other direction, we can also expand logarithms. Okay, sometimes we'll find it useful to take a collapsed down logarithm and expand it out a little bit. Okay, so when we say that, it means we're going to write the logarithm of a product or a quotient as the sum or difference of logarithms. So in example 5, this one's pretty straightforward. All we're saying is if I have the log base 5 of 10x, it's okay to write that as the log base 5 of 10 plus the log base 5 of x. Now you might wonder, okay, what's the point of all this? One example I would give you is that suppose that I'm thinking of this as the graph, so I'm thinking of y equals log base 5 of 10x. What this tells us is that when I write it like this, 10 tells me I have a horizontal shrink of the graph of log base 5 of x. But then when you expand it out, that shows you that you have a vertical shift of the log base 5 of x. So kind of find an interesting little property there that horizontal shrinks or stretches can always be turned into vertical shifts. So kind of maybe an unexpected thing about logarithmic graphs. All right, and then if I have one like this, the natural log of x cubed times y to the 4th, then we'll go ahead and start off with property number 5, which just says the product is the same as adding the separate logarithms. But then we'll also take another step. We'll also use property number 7 so that I just have the sum of logarithms without any powers inside those logarithms. So anytime we want to expand it, we'll want to take this step as well. All right, here's just a bit harder of an example. So when we start off with something like this, you see that there's multiple x's and multiple y's in this expression. So what we probably want to do here is before we jump into the properties, just go ahead and simplify this whole thing a little bit. So first of all, if I'm taking x times y times this fraction, we know really this can be x times y over 1, right? So the numerator inside the logarithm can become 5x squared y. And then this square root of y on bottom we know is also the same as y to the 1/2. And so with our exponent rules, we know that we can combine this y and this y to the 1/2 by understanding this is y to the first up here. And when you divide like bases, you are going to subtract exponents. So 5x squared y to the 1 minus 1/2. So this will be the log of 5x squared y to the 1/2. But now this is just a product of three different expressions. And so even though our property only says what to do about multiplying two things, I don't think it requires a big leap of logic for us to just say that if we're multiplying three things, then we can just add those three things separately. And then my last step here is these two that have exponents. Let's take care of that with property number 7 and say that exponent can come down and multiply by the log of x, and the 1/2 can come down and multiply by the log of y. So lastly, we're going to address the last property, the change of base property, which says that I can if I take any logarithm, doesn't matter what it is, let me rewrite it here, the log base b of a, then what I can do is pick any base I want. We'll call it c, and say that that's going to be equal to the log base c of a divided by the log base c of b, what your base was originally. Now here's why this is so powerful. If I look on my calculator, most calculators only have two log buttons, the natural log and the common log. They don't necessarily have an easily accessible way of calculating, say, the log base 3 of 5. Okay? So there's no button for log base 3. So this gives us a way of computing what log base 3 of 5 is. What it's saying is I can just take the natural log of 5 and divide it by the natural log of 3. And there's that answer that I gave right here. And it works for any logarithm, right? So when I do the log of 5, that should be equivalent to the log of 3. Same answer. Okay, so this is really powerful for us. So anytime you need to compute a logarithm, then you use this change of base formula to do it. And then we can even sketch graphs on our calculator of logarithms with various bases. So if I want to take a look at f of x equals the log base 5 of x on my calculator, then I know that in my calculator I can just type the natural log of x divided by the natural log of 5 into my y equals menu. So if I do that, natural log of x divided by the natural log of 5, and I hit graph, then that graph is a graph of this logarithm.